In Chapter 1a, we introduced the ideal gas law, which is a limiting law, meaning that the law is only valid when the pressure approaches zero. Now in Chapter 1b, we use the kinetic model to show that ideal gas is just a collection of dots moving randomly in all directions with no intermolecular interaction. Now in reality, even for gas molecules, there's the intermolecular interaction do exist. And here shows a diagram of the potential energy as a function of internuclear separation. Potential energy is a measure of intermolecular interaction. When the molecules has no intermolecular interaction, the potential energy will be zero. So looking at this diagram, we can see here at far intermolecular separation, the potential energy is zero. So this is when the molecules behave as ideal gas. When the molecules approach each other, the distance becomes smaller and the potential energy decreases. When the potential decrease becomes lower, that indicates molecules start to feel attraction force between each other. So the attraction force dominate. Now, when the molecules get too close to each other, repulsion force becomes dominate, and then the potential energy start to increase. So in real gas, two types of intermolecular interactions exist: attraction force, repulsion force. Which one dominate depends on the internuclear separation. Let's plot PV isotherm for a real gas, for example CO2, at 25 degrees. Now, if carbon dioxide behaves as ideal gas, then the PV curve should show a hyperbola: increase pressure, decrease volume, and that's the Boyle's law. Now, indeed, we see a range where carbon dioxide behaves as ideal gas, obeys Boyle's law: increase pressure, decrease volume. However, when the pressure increases enough at this point B, now it starts to deviate from this Boyle's law. Okay, so deviate from the Boyle's law above the point B. And when the pressure is high enough at the point C, then the volume of CO2 suddenly decreases to E. So what happens at C? Okay, you see the flat line. So what happens at C? It turns out that at this point, the molecules are so close together, attraction force is large enough to change gas phase becomes a liquid phase. So the point E is a liquid phase. So now, if you want to reduce the volume of the liquid, you need extremely high pressure. The fact that carbon dioxide change from gas phase to liquid phase at high pressure is an evidence of intermolecular interaction in real gas. In the last slide, we showed a PV curve for carbon dioxide at 20 degrees. So here we show more curves at different temperatures. So any temperature below 31 degrees, we always see two phases. For example, liquid phase and gas phase. Liquid phase is characterized by a low, small molar volume. Small molar volume means large density, so high density. And gas phase has a large molar volume, which indicates a small or low density. And that's one of the difference between gas phase and liquid phase. Liquid has a higher density, gas phase has a low density. All right. Now, at 31 degrees, we see an inflection point. Above 31 degrees, then, for example, 50 degrees, we only see one phase. There's no difference between liquid phase and the gas phase. There's only one phase, and this phase can have high density like liquid, or can have very low density like a gas phase, and this is called supercritical fluid. So for carbon dioxide, above 31 degree, it forms a supercritical fluid. Below 31 degree, there's always two different phases, liquid and gas phase. And 31 degree here, you have an inflection point, and this point is called critical point, and the temperature in this case is 31 degree is a critical temperature, and the volume is called the critical volume, pressure is called the critical pressure. So the critical constant is unique for different substances. And we'll see in the next slides more about the different substances. This table shows critical constant for different gases. We already see in the last slides, carbon dioxide has a critical temperature 31 Celsius, which is 304 Kelvin. Oxygen has a critical temperature 154. So if we want to make oxygen liquid oxygen, temperature must be below this temperature. Otherwise, it's always one phase. This diagram shows different phases of carbon dioxide. And you can see clearly the difference between gas phase and the liquid phase. Liquid is more dense, and therefore it's on the bottom, and the gas is lighter, it's less dense, it's on the top. So gas phase, liquid phase, gas phase, liquid phase. Until it becomes supercritical, then the gas phase, liquid phase difference disappear. It becomes a single phase. The deviation of an real gas from ideal gas can be measured by compression factor. Compression factor is defined as the volume of the gas divided by the volume if the gas behave as ideal. So in this equation, this is the molar volume of 1 mole of the real gas, and this is the volume if the gas behave as ideal. So here you have a knot to represent this is ideal volume. Now we learned ideal gas law. One way to write is PVM equals RT. Okay, so if gas behaves ideal, that's the law. Now, however, at this point, the ideal volume should use a knot. All right, so the equation should be written as PVM knot. Okay, because this equation only for ideal, and this symbol represents the ideal volume. Now, from this definition of Z factor, we can modify this equation to find the relation between V naught and V. So V naught should equal to Vm divided by Z, right? So you just go up and this Z goes down. All right, so V naught should equal to Vm divided by Z. Now plug in here, okay? So what you get is P Vm divided by Z equals RT. And then both sides times Z, what we have is PVM equals ZRT. So compare ideal gas law. This is ideal gas law, and this is gas law we just derived from real gas. In fact, this equation can be applied to any gas, can be ideal or non-ideal. If it's ideal, then Z is 1, and that go back to this equation. All right, so PVM equals ZRT. So if Z is 1, that's ideal gas law. If Z is not, if it's real gas, then you need to find the Z factor. So if we have the Z factor for a real gas, then we can just as if using the ideal gas law, we can calculate the volume or pressure or temperature if we know other parameters. This is a diagram shows the Z factor of different gases when the pressure changes. At a very low pressure, you can see if you enlarge it, all gases, whether it's hydrogen, methane, ethane, or ammonia, they all merge into one number, and that's 1, which is not surprising because at a very low pressure, gas behaves as ideal gas, and Z is 1. Now, at very high pressure, here, okay, extremely high pressure, because pressure is so high, then gas molecule becomes so close to each other, repulsive force dominate. Now, when repulsive force dominate, the real volume will become greater than if it's ideal volume. So Z factor is greater than 1. At moderate pressure, attraction force dominate, and that will brings real volume less than the ideal volume. So Z becomes less than 1. As I mentioned before, gas is described by pressure, volume, temperature, number of moles. But these 4 parameters are not independent, but related by an equation and called the equation of state. Ideal gas law is one of the equation of state. For real gas, there are several equations of state. One way to modify this ideal gas law, but add more terms here in terms of pressure. As we know, pressure is responsible for the deviation of ideal gas, real gas from ideal gas. Now we also know pressure is inversely proportional to volume, so this equation we can also written as here, inverse volume, inverse of volume squared. Now if we only include the first term here, 1, that is just the ideal gas law. Now if we add more terms, that will make it more accurate to describe real gas. But in most cases, the second term is enough to describe a real gas. The B is called the second viral coefficient. This table shows a list of second viral coefficients for different gases. And note that the coefficient changes when temperature changes. So if we only include the second viral coefficient, the equation of state becomes this. So if we plug in B, then we can use this equation to calculate either pressure or volume or temperature. Here's a sample question. Calculate pressure exerted at 100 Kelvin by 0.104 mole of oxygen in a vessel of volume 0.225 cubic decimeter using viral equation of state. In order to use equation of viral state, we need to know the molar volume. So we use the total volume divided by number of moles. So calculate molar volume, all right, and change cubic decimeter to cubic meter, and then that's the viral equation of state. So the molar volume is just calculated, temperature is given, is here, and we need to know the B. So B can be found from textbook. All right, so here for oxygen is 1.975 times 10 to the minus 4 cubic meter per mole. So plugging everything, the calculated pressure is 3.5 times 10 to the 5th Pascal, which can be converted to 350 kilopascal. Now, if we assume this gas is ideal, using ideal gas law, the calculated pressure should be 385 kilopascal. Since ideal gas has no intermolecular interaction, but the real gas do have intermolecular interaction. If we add this interaction into ideal gas law, we may be able to derive an equation of state for non-ideal gas. So let's look at the consequence of these intermolecular interactions. First, let's look at the repulsive force. Okay, if molecules have repulsive force between them, then let's say this is molecule A. So there is a volume around A that other molecules cannot go. Okay, so it's not available to other molecules because they repel each other. Similarly, for B, molecule B, A cannot go through this volume. Okay, so if V is the container volume, the free volume for the molecules to move is much less than that. So the free volume can be calculated by the container volume minus constant B. B represents the volume that is not accessible to other molecules due to the repulsive force. And then you times the number of moles. Okay, it's the more molecules you have, the more volumes that are not available for other molecules to go due to the repulsive force. Okay, so if we think about ideal gas law, PV equals nRT, this volume should be the volume that available to all molecules. So instead of use the container volume, we should use V minus NB. And that's the consequence for repulsive force. Now let's look at attraction force. So here we know that molecules constantly strike a wall. That's the reason for the pressure. Okay, pressure is due to the constant movement of the gas molecule that strike the wall. Now, if molecules attract each other, so if these two molecules attract each other, then this molecule has less force to strike the wall, and that will reduce the pressure. Okay, so reduce pressure by how much? Well, first, it will reduce the force. Okay, reduce the force proportional to the density of the molecules. So the more molecules you have, the less force it will strike the wall, and so it is proportional to the density, which is N divided by V. Now the attraction force also reduces the frequency. Every second, how many times it strike the wall also is reduced by proportional to the density, again N divided by V. So the force or the frequency combined together, and the pressure reduced by V divided by N squared. Okay, squared because not only force is reduced, the frequency is also reduced proportional to the density times a constant A. Okay, A is constant that unique to different gases called van der Waals constant. Similarly here, the B is also called the van der Waals constant for different gases. A, B are different. So here we see that if we add the attraction force, the pressure will be reduced, and therefore we have to modify the ideal gas law by adding repulsive force and the attraction force that we'll see in the next slide. Let's start with ideal gas law, PV equals nRT, or we can write as P equals nRT divided by V. Now for real gas, we just showed that there are attraction force, repulsive force. Repulsive force reduces the volume, so we need to change the volume. And attraction force reduce pressure, so you should minus how much pressure is reduced. All right, so let's add these two. First, the volume, free volume is reduced by MB, so minus MB. This is due to the repulsive force. And the pressure is reduced by the density squared times A. Okay, so one is due to the repulsive force, this is due to the attraction force. Now, this equation is suitable for real gas. Okay, it's based on ideal gas, but we add attraction force and repulsive force, and this equation is called Van der Waals equation. All right. Now another way to write Van der Waals equation is to remove number of moles. To do that, we can divide by a fraction, divide by n. So for example, the first one, nRT, V minus NB. If we divide by n, numerator, denominator both divide by n. So the top n cancelled, you get RT. The bottom V divided by n is molar volume. So this one becomes molar volume minus B. Okay, so that's the first one here. All right, we don't have number of moles. And the second one, n divided by V density squared, you can also divide by n, divide by n. So the top is 1, the bottom is molar volume squared. All right, so you get A divided by Vm squared. And so the good thing for the second equation is that you don't have number of moles. You don't need the number of moles. You can calculate the molar volume. Or if you know molar volume, you can calculate the pressure. So both of these equations are called Van der Waals equation. This table lists Van der Waals constant for different gases. A represents the strength of attractive force, and B the strength of repulsive force. In fact, MB is the total volume taken up by the molecules themselves. All right, and for ideal gas, it's just dots moving, so MB must be very, very small compared to the container volume. In this sample question, the nitrogen temperature is given, molar volume is given. It asks you to calculate the pressure. First treat it as ideal gas, and then use the Van der Waals equation. So for ideal gas, we use ideal gas law. PVM equals RT. P equals RT divided by VM. And note that the molar volume here in terms of liter, and 1 liter is 1 cubic decimeter. All right, and so so if we use liter, the R constant we can choose is 0.08314 liter bar per mole per Kelvin. So the answer will be 249 bar. All right. Now Van der Waals equation. In this equation, A, B are given. Note that the unit is cubic decimeter, but the same as liter. And so plug in all the data. What we get should be 270 bar. So compare to the ideal gas, okay, the pressure is 270 compared to 249. So pressure is greater than the ideal gas, and that indicates it is the repulsive force dominate. Okay, because if it's attractive force, then you can expect the pressure should be smaller, should be reduced due to the attractive force. The fact that it's greater than the ideal gas pressure means repulsive force dominate. Here is a 3D plot of pressure as function of volume temperature using Van der Waals equation. At high temperature, ideal gas isotherms are obtained. At low temperature, we see Van der Waals loop. Okay, now experiments show that at low temperature, you should see a flat line, so the gas phase becomes liquid phase. And this can be corrected when we add flat line so that the two areas are the same. Now, one application of this Van der Waals equation is to find the critical points. And the critical point is when the curve has an inflection point. In calculus, the inflection point inflection point, the first derivative and the second derivatives are both zeros, and we're going to see in the next slide. To calculate the critical constant, we write a van der Waals equation and set the first derivative, second derivative, both zeros. And the solution gives you critical volume 3b, critical pressure A divided by 27b squared, and critical temperature 8A divided by 27b R. Okay, so these are the theoretical prediction of critical constants for real gas using van der Waals equation. Now, one interesting result is when we calculate the Z factor at the critical point. Now, for any gas, we can write as PVM equals ZRT. So if it's ideal gas, Z is 1. If it's non-ideal gas, then Z is not 1. All right. So Z can be calculated by PVM divided by RT. At the critical point, all right, the pressure should be critical pressure, volume should be critical volume, and temperature should be critical temperature. So plug in all these constants, and what we find is 3/8. And the interesting feature is that this critical constant, the Z factor at a critical constant, has nothing to do with the van der Waals constant A, B, C. In other words, any gas, real gas, they should have the same critical, same Z factor at a critical point. So the van der Waals equation predict that all gases near their critical points should give you the same Z factor, about 0.375. And this matches experiment reasonably well. So this table lists some equations of states. We already introduced the ideal gas law, the van der Waals equation, the Waals equation. We don't have time to go to other equations, but let's focus on van der Waals equation and derive an interesting equation in the next slide. We have seen that critical constants are characteristic properties of gases. So now we define reduced variables by using pressure divided by critical pressure, and that's called reduced pressure, volume divided by critical volume, which is called reduced volume, and the temperature divided by critical temperature is called reduced temperature. And let's see what we can do with these reduced variables. Okay, so here is the van der Waals equation. So note that in van der Waals equation you have van der Waals constant A, van der Waals constant B. That means different gases, even if they have same temperature, same volume, the pressure will be different because A, B are different from gas to gas. However, if we replace the volume by reduced volume, temperature replaced by reduced temperature, pressure is replaced by reduced pressure, we get an equation now similar to van der Waals equation, but not exactly same. You don't have A constant, you don't have B constant. And that means all gases, if we use reduced variables, then they becomes the same equation. Same volume, reduced volume, same reduced temperature give you same reduced pressure, all right, for different gases. Okay, so this is summarized by the principle of corresponding states. It says all fluids behave similarly when described in terms of their reduced temperature and pressure. Okay, it's reduced temperature and pressure. Here shows the application of principle of corresponding state. We have seen this diagram already before. This shows the Z factor as a function of pressure. So at a very low pressure, all gases, Z factor is 1. But when you increase pressure, they deviate from 1. Now, if you replace the pressure by reduced pressure and the temperature by reduced temperature, then you can see the curve, all gases merge into the same curve. For example, here, nitrogen and methane, they are in the same curve. If they have same reduced pressure, reduced temperature, they give you same Z factor. Okay. Similarly here, this is the temperature is reduced temperature 1.2, and this is reduced temperature 1.0. So the property of a range of gases can be correlated onto a single diagram. So the advantage is that you don't need to think about whether it's hydrogen, nitrogen, or methane. All you need is use the same curve. All right, find the reduced pressure, reduced temperature, and then you can find the Z factor. Here are two sample questions. Question 1. The critical constant for argon carbon dioxide are given in table 1C2. Suppose argon is at 23 atmosphere. So that's the pressure and the temperature for argon. Calculate the reduced pressure, PR, and TR, reduced temperature. So according to the definition, PR, reduced pressure, is the pressure, which is this one, divided by critical pressure, and the temperature, reduced temperature, is the temperature divided by reduced critical temperature. So first find the critical pressure, critical temperature from textbook for argon, and then calculate reduced pressure, 23 divided by 48, give you 0.48, and the reduced temperature 1.33. Next question, calculate the pressure and the temperature of carbon dioxide for it to be in a corresponding state. In the corresponding state means the carbon dioxide has the same reduced pressure, reduced temperature as the argon. So in this case, we know the reduced pressure, and we want to calculate the pressure, but we need to know the critical pressure. So if we know critical pressure, then the pressure can be calculated by reduced pressure, which is 0.48 times critical pressure. So find the critical pressure, critical temperature for carbon dioxide, and then calculate the pressure to be in the corresponding state, which is reduced pressure times critical pressure, will give you 35 atmosphere. Similarly, the temperature is critical temperature times reduced temperature, and that will give you 405. Here's a sample question of using Z factor and principle of corresponding state. We want to calculate the molar volume of carbon dioxide if we know temperature and pressure. Okay, to do that, we use the equation PVM equals ZRT for a non-ideal gas. And to calculate ZM or VM, we first need to know the Z factor. Okay, so here is a plot of Z factor as a function of reduced pressure, reduced temperature. So these numbers are reduced temperature. So in order to find the Z, we need to calculate reduced temperature, reduced pressure. So we know temperature, all right? We need to know the critical temperature and the critical pressure. And find the carbon dioxide, we already know from the last slide. We know the critical temperature, pressure, so we calculate this is the reduced temperature, reduced pressure. Okay, so when reduced pressure is 1, and that's here, and reduced temperature is 1.5, and somewhere here. Okay, and so that give you this point, and that point corresponds to z factor 0.92. Okay, so with this z factor goes to here, we can calculate the molar volume. All right, so molar volume is z times RT over P, and that gives you 472 cubic centimeter per mole.